So functions. What on earth is a function? Well, first of all, let's start with a different definition, and that's relation. So a relation is simply some rule that maps between two sets of values. So for example, something like this. Whoa, what a mess. So we can see that over here in the x's, the -1 is mapping over to, let's follow it. Is it mapping over to anything there? Looks like it's going to -2 over there, doesn't it? But there's all sorts of mapping happening there. In fact, that is the relationship. X squared plus y squared equals 5. If you were to follow all those arrows, you'd find they all obey that particular rule. X squared plus y squared is equal to 5. So that's a relation. So basically a relationship exists. You can write down a formula that will link the values together. Now we're really interested in functions, and that's a special type of relation. Okay? But it uniquely maps from one set to the other. So the mapping is unique. So in this case, the x's are all being uniquely mapped over to the y's. So -2 is going to 4, 2 is also going to 4, and 1 and -1 are both going to 1. That one has a relationship y is equal to x squared. So each one of those y values is the x value squared. The independent variable you can think of as the input of the function. So it's like free choice. You can pick what you like. That's why it's independent. I'll pick any x value I like, and I'll sub it in. Now, domain then, sometimes called the natural domain, is every possible value that you could substitute into this function. Right? So all the possible independent variables. Now, restricted domain, sometimes we have to restrict the domain in order to get a function. Right? Also, see, domains are restricted. Some values also are not required. If I look at my hyperbola over here, y equals 1 on x equals 0 is not required. It won't map. We can't substitute in 0 and get an answer. So sometimes our domain's not anything you like. It's restricted. It has some sort of restriction on it. What's the example I put there? If the independent variable represented time, then we'd only have t is greater than or equal to 0. Unless you believe in time travel, I suppose. Now, the dependent variable then is the output. Its value depends on what you substitute in. So that's what we call the dependent variable. And so when you're drawing your graph, the independent variable always goes on the horizontal axis, and the dependent variable always goes on the vertical axis. Range then is all the possible outputs, all the possible dependent variables. If you were to substitute every possible variable from the domain, if you were to substitute it in, all the possible answers you would get. And that's the range of the function. So notation. I'll see something like this. Y equals, and F is probably the most common letter we use. I guess F being function. But it doesn't have to be F, it could be anything. It could be G, it could be H, it could be a Greek letter. But basically the independent variable is what we're substituting in, and F is representing the function, and the dependent variable, that's the subject of the formula. So function x might equal 3x squared plus 4. If I wanted to work out function 5, it's basically just saying, hey, substitute 5 in. What are you going to get? Sub it in, 79 in this case. You don't have to substitute in numbers. I could substitute in a pronumeral. So function a, everywhere I see an x, I'm just replacing it with an a. So that's 3a squared plus 4. In fact, it doesn't have to be a single term. I could have function x plus h. From that, I'll subtract function x. So everywhere I see an x, I'm putting x plus h. So it becomes 3 lots of x plus h squared plus 4, and then I'm going to subtract function x, expand out, tidy up, I get 6xh plus 3h squared. Now, how do I tell whether something is a function? And the easiest way is by looking at the graph itself. If you look at the graph, you can use a vertical line test. Because the values of x are unique, then what should happen is if I draw a straight line parallel to the y-axis, I should only cut the graph once, if at all. I mean, it might not cut it at all. If it cuts it more than once, then I know it's not a function. because I'm not getting a unique answer for that x value. So for example, here's our hyperbola. It does not matter where I was to draw a vertical line, let's put it there, it's only going to cut it once. Other than at x equals 0 where it doesn't cut it at all, but that's fine. So yes, big tick, that is a function. Parabola on its side. Well, if we start out at the left-hand side, everything's fine. It's not cutting at all, that's good. We get to the y-axis, it'll only cut it once. Fine, it's still satisfying our rule, but as soon as we move into the positive values, doesn't matter where I put that vertical line, cuts it twice. No good. So no. That's not a function, that would just be simply a relation. Actually, this one over here, x equals y squared, is made up of two different functions. And you'll find that with those symmetric type shapes on their side. One is the positive square root of x, one's the negative square root of x. When it comes to the circle, one would be plus the square root of r squared minus x squared. One would be minus the square root of r squared minus x squared. So again, made up of two different functions. So let's talk a bit about domain and range then. How do we find the domain and range? Again, if you've got the picture, terrific, because you can just look at the picture and you see what x values are giving us an answer. So there's the parabola on its side. Even though it's not a function, it still has a domain and range. So the domain, I can see, well, it's going to be x is greater than or equal to 0. That's the only thing that's producing answers. You might have one of those split functions, step graphs and things like that. So what about this one? Well, it'd be x is less than or equal to 0, but we also have x is greater than 2. Okay, I haven't got the picture. What do I do? So all I'm seeing is the algebra, the equation. Things to look for, things we know. Fractions. Well, I know the bottom of a fraction can't equal 0. So that's going to cause problems. So there's our hyperbola again. I see that, and let's pretend I have no idea what that looks like. I'd be saying, well, hang on, the bottom of the fraction can't equal 0. So therefore I know x can't equal 0. Now that's not the domain, but that's going to help me find it. Because a domain is inclusive, not exclusive. Oh, is that the right word? Exclusive if you're not including it? But anyway, the domain is all the things that you can have, not what you can't have. So I would write it something like that. Oh, well, everything is possible. All real x, except I can't have x equals 0. So if I had something like 1 on x squared minus 1, again, I'm looking at it, fraction. That bottom of the fraction may cause me problems. I know x squared minus 1 can't equal 0. So x squared's not 1. Therefore, x can't equal plus or minus 1. I won't get answers if I try and substitute those in. So I'd have, well, all real x except for those two values, plus or minus 1. Two fractions, well, I look at both denominators in this case. So I know x minus 1 can't equal 0. So there's one exclusion. And 7 minus x can't equal 0. There's another exclusion. So all real x's except 1 and 7 in this case. Root signs. When I say root signs, I probably mean even root signs. The odd ones are fine because you can't find the square root of a negative number. We know that. And any even root, you can't do it to a negative number. Cubics, you can. If I said, what's the cube root of negative 1? Oh, it's negative 1. We can find that. But any time it's an even one, you can't. And square roots are the most common ones that we see. So again, let's pretend we don't know what that looks like. So I'd say, oh, all right, well, hang on, I can only find the square root of something that's greater than or equal to 0. So 4 minus x squared is greater than or equal to 0. That means x squared is less than or equal to 4. Hang on. Must be in between minus 2 and 2. So it must be in between minus 2 and 2. If I have 2, well then again, both of these have to satisfy that rule. So I know x plus 3 is greater than or equal to 0. 5 minus x is greater than or equal to 0. So I'm looking for numbers that are both greater than or equal to minus 3, but also less than or equal to 5. Well, it must be all the numbers in between those then. So minus 3, less than or equal to x, less than or equal to 5. Ooh, let's combine the last two ideas. I've got a fraction and I've got a square root sign. So bottom of the fraction can't equal 0. But the third has to be greater than or equal to 0. So combine the two together, that means instead of x plus 2 being greater than or equal to 0, It's just greater than, because it can't equal 0. So x plus 2 is greater than 0, so x will be greater than minus 2. Well, what about range? Again, if we can see the picture, nice and easy. Imagine you're climbing up the y-axis and you're just looking over and going, can I still see the shape? Yep, still there. Climb up some more. Yep, still there. Climb up some more. Yep, still there. There are no breaks in that curve at all. So the range would be all real values of y. Now, it's important you mention that they're real numbers, by the way, on something like this, because there are such things as imaginary numbers. Right, so we specify, yep, they are the real numbers is what we're interested in. Back to our split function. So for that one, what do we got? Less than or equal to 1, greater than 3. But again, we don't know what the picture looks like. So what are the things that we look for? Maximum, minimum values. Right? You see, even powers, absolute values, things like that, we know they always have to be positive. And so that can give us a clue as to how high or how low the function might go. So y equals x squared. Again, pretend we don't know what it looks like. So, well, the range would be y is greater than 0, because I know x squared will only produce things that are greater than or equal to 0. If it was x squared plus 3, well, I know the x squared will produce things that are greater than or equal to 0. So in this one, y is going to be greater than or equal to 0 plus 3. So we get y is greater than or equal to 3. 5 minus x squared. Okay, so x squared has to be bigger than or equal to 0. But if I'm taking the negative of that, it's like turning the thing upside down. And now I know the biggest it can be is 0. In other words, that one has to be less than 0 or equal to. But we also have the 5 there as well. So it's going to be 5 minus 0, which is, of course, 5. Absolute value, same idea. We know the absolute value always has to be a positive number. So that range would be y is greater than or equal to 0. If I was to subtract 5 from it, again, same idea. That y would have to be greater than or equal to 0 minus 5. So, negative 5. Restrictions on the domain. So maybe you've found the domain and you've worked out there are some restrictions, like, say, the hyperbola. We found out, oh, hang on, x can't equal 0, or things like that. So if there's restrictions in a domain, a general idea is to have a look at the endpoints of the domain if it has them, like it's not going off to infinity. So have a look at the endpoints, and it's amazing how many of these things are symmetric. So maybe have a look around the middle of the domain as well. So let's go back to square root of 4 minus x squared. Again, pretend we don't know what the shape is. We restricted the domain. We said it's in between minus 2 and 2. Well, let's see what's happening. Out at the endpoint, I get a y value of 0. Now, I don't know, did I bother something in minus 2 as well? Because x is squared in this case, so clearly I'm going to get the same answer. But in the middle, I get an answer of 2. So a pretty good bet would be y is going in between 0 and 2. And of course, if you're ever unsure, you go to calculate. There's nothing stopping you subbing some numbers in and going, oh, yeah, okay, let's just check some of these numbers and see if it's working. Fractions. So back to our idea with fractions. If you have a constant on the top of a fraction, then that fraction can't equal 0. Because it is impossible to divide a number by something and get the answer of 0. You can't do it. So back to our hyperbola. Well, y can't equal 0 because that fraction can't equal 0. But again, a range is talking about what's included, not what's excluded. So it'll be all real y, except y can't be 0. 5 plus 1 on x then, very similar to what I was doing before. Well, I know the fraction can't equal 0, so therefore we get a range, all values except 5. This one's a little bit more involved. X plus 7 on x plus 4. What do I do here? Well, what I do with this one is a polynomial division, I suppose, is what I'm doing. But I'm rewriting that fraction as 1 plus 3 on x plus 4. Now I've got a constant on the top of the fraction. So I know that fraction can't equal 0. So if you're unsure, you could, you remember polynomial division from polynomials? I mean, it's a very simple one, of course, but you can always go back and go, all right, let's calculate it out. So all right, we now know y can't equal 1 plus 0. So all real x except y is equal to 1. All right. Woo.